Welcome back to the workshop. We want to look at another example of determining the radius of convergence and the interval of convergence for a power series. So we use the same steps that we used in the last video, determining the center where the power series is centered, then determining the radius of convergence, and then finally testing the endpoints to determine the interval of convergence. So let's start with identifying where the series is centered. It's pretty clear immediately that the series is centered at 4. So the series is centered at c equals 4. So that's our first step. Our next step is to use the ratio test to determine the radius of convergence. So we want to find the radius of convergence. Now, I say that we want to use the ratio test. It's also possible that you might want to use the root test or the integral test or some other test that gives conditions for the convergence and divergence of a series. So for the examples that we will be taking a look at, that you can take a look at with me, we'll use the ratio test in each case. But be aware that it is possible that other tests could be used to determine the radius of convergence. You may have already seen this. Likely you'll see some other example at some point where you're expected to use the root test. At least if you're one of my students, there's a nice hint for you. So for now, radius of convergence can be determined using the ratio test. So let's take the limit as n goes to infinity of u sub n plus 1 divided by u sub n. Of course, we want absolute values in this case. And then from here, instead of taking our fraction and dividing by a fraction, or our rational expression rather, what I'd like to do is I'd like to take the numerator and multiply by the reciprocal of the denominator. So we can see that this is equal to the limit as n goes to infinity of, now since I'm concerned with the absolute values, I do not need this negative 1 to the n plus 1 because it's either going to be negative and it does nothing at all because we're taking the absolute value, or it's going to be positive and again does nothing at all. So I'm just going to ignore that, and we have x minus 4 raised to the n plus 1th power divided by n plus 1 times 9 to the n plus 1. Then we multiply by the reciprocal of the denominator, multiply by the reciprocal of u sub n. So the denominator of that denominator. So in the denominator we would have this entire thing. So I'm going to write this on top, n times 9 to the n. And I'm going to write this on bottom, again ignoring the negative 1, that's not going to do anything. So x minus 4 to the n. Excellent. So now I can do a little bit of simplification. So this is equal to the limit as n goes to infinity. Let's see here, x minus 4 to the n plus 1, and x minus 4 to the nth. There would be some simplification there, some cancellation. So we're just left with x minus 4 in the numerator. And then we still have a factor of n because that does not cancel out with anything in the denominator. Still a factor of n plus 1 in the denominator. Again, doesn't cancel out with anything. And now we just need to reduce the powers of 9. So n factors of 9, n plus 1 factors of 9 gives us 1 factor of 9 in the denominator. I still want the absolute value of all of this, because x minus 4 may be positive or negative. Of course, n plus 1, and 9 are all positive. Alright, so a little bit more work here. So let's take the limit as n goes to infinity. Well, actually, before I do that, again, x minus 4, this thing here does not depend on n. So I can actually take that outside of the limit. So the absolute value of x minus 4, because that's the only thing that could be negative here, times the limit as n goes to infinity of n divided by n plus 1 times 9. Excellent. Again, no absolute values inside because each of these factors is positive. All right, so now that I'm there, let's see here. The limit of this guy is 1/9. So this is equal to 1/9 of x minus 4. That tells us that the series will converge when this is less than 1. So by the ratio test, the series converges for 1/9 times the absolute value of x minus 4 less than 1. That is the absolute value of x minus 4 less than 9 by multiplying both sides of the inequality by 9. And the radius of convergence is r equal to 9. Alright, so we have found the radius of convergence. The last step is to test the endpoints. Again, our interval is going to look something like c minus r to c plus r, and I need to determine whether I'm going to use parentheses or brackets in each case. Could be brackets on both sides, could be parentheses on both sides. Right, there are several possibilities there. All right, so test the endpoints. Those endpoints are exactly x equals 4 minus 9, which is negative 5, and x equals 4 plus 9, which would be 13. So when I'm using x is equal to a negative 5, I get negative 5 minus 4 here, which gives me a negative 9 to the nth power. So I've got the series, let's see here, negative 1 to the n plus 1 times negative 9 to the n over n times 9 to the n. I want to simplify this expression a little bit. When I do that, it will make much more clear the convergence or divergence of the series. So this is equal to the sum. Let's see here. This is actually negative 1 to the nth times 9 to the nth. So negative 1 to the nth power times negative 1 to the n plus 1th power gives us negative 1 to the 2n plus 1. So that, in fact, is actually just negative 1, because 2n plus 1 is always odd. Negative 1 to an odd power is always negative 1. That left us with 9 to the nth power, which would completely cancel with 9 to the nth power. So this is simply the sum of 1 over n, which diverges since it's the harmonic series. Of course, it's the negative version of the harmonic series. All right, testing x equal to 13 gives us, now we have 13 minus 4 would give us 9 to the n. So negative 1 to the n plus 1, 9 to the n divided by n times 9 to the n. Again, the 9 to the n's will cancel out, and we're just left with negative 1 to the n plus 1 over n. So this is the sum of negative 1 to the n divided by n, which converges because it's the alternating So at this endpoint, we do not include, and at this endpoint, we do include. So this gives us that the interval of convergence, is, let's see here, we do include that, sorry, we do not include that endpoint, so that's -5, we did not include, and here at 13, we do include that because the series converges, so the interval of convergence is from -5 to 13, where we do not include -5, and we do include 13. And that looks good. You might be able to see I wrote down the solution, or the answer right down here, to make sure that I got the right answer at the end. I did. Excellent. All right. Thank you for joining me in the workshop. There will be at least one more example coming up for this, possibly 2 more examples. So keep an eye open for that. Again, thank you, and I'll see you guys here in the workshop again soon.